So we start our discussion of the third part of the course, which is called, in general terms, balance laws. And what we are going to look here more precisely is that we will see how basically very briefly we will look into the conservation of mass. So basically stating that looking into what equations that we need to satisfy in regard to that physical observation that mass is conserved if we don't have a source for that, or if if we don't consider an open system where the mass can come in. But we'll talk about that a little bit very shortly soon. And so there are also the balance laws. Basically, we need to consider two balances for the linear and the angular momentum. And so that will equip us with a set of equations that we need to satisfy for our system, differential equations. At the end, what will be most useful for us is the the so-called equilibrium equation that stems from the linear momentum balance, the second one. They're equally important. We'll need to satisfy all of them, but we'll see that again. You probably already heard that the angular momentum just provides us the information about the symmetry of our certain stress measure, of the true stress, and so we are using that to reformulate the linear momentum and equilibrium equation at the end. So all of them will be included in important. Now, of course, this is already a description of the physics, let's say. So this physical and this physics laws. So they are based on some observations, or if you want, some experiments, right? So this is so it's a little bit as opposite to the more mathematical and more abstract description of kinematics that we just previously had. All right. So our first consideration is we'll consider conservation of mass. So because before we go into writing the equations for that to preserve mass, so we'll just take a little very short detour, and with the motivation in mind that mass is a scalar, right? So now we'll need to deal with with calculating how this scalar changes, and we will need to integrate things and then to calculate the rate of change. And so therefore we are going to look first in the in the mathematics behind that, how we deal with the material time derivative of such integral measure. So that will be our first order of business for today, for this part. And so again, we consider the material time derivative. And now we have a scalar that we're going to take this material time derivative of, but well, the scalar is an integral itself, right? Again, so what we have in mind for that is that we take the integral of a density over the volume, and that will be our mass. So writing this in an integral way. But to proceed with that, we just first consider any scalar function. Now, so let's say we're considering the a spatial description, right? So it's meaning that our function, the scalar function psi, is a function of y and t. So basically, in our spatial, in the deformed or in our current configuration, right? So now we're taking the material time derivative, where we say typically, right? So that's to distinguish it from the spatial time derivative, that we fix the x as an independent variable. So this is fixed. And so now we need to deal with that. So we take this the material time derivative of this integral. And now, so what we need to deal with is that, okay, so there's not only that function psi that is dependent on t, right, but also that volume of that that we integrate over is also dependent on t. And so then therefore we need to, and that's emphasized here, right, so this is emphasized here that this dv that volume element differential is a function of t, right? So then we need to take this into account. So, and that was and so we write this dvt more explicitly in terms of basically multiplication of dy1, dy2, and dy3. Right, so again, just remind you that these are meaning that this is the volume element in the deformed or in the current configuration, our special description. Right, so then so then basically then we can see that there is 1, 2, 3, and 4 multiplicators here. So we take the time derivative of all these 4, and so we have 4 terms, right? So first we take the derivative of psi and multiply it with dy1, dy2, dy3, so we don't touch them. Then we take the time derivative of dy1 and then it will be multiplied by psi dy2 and dy3 and etc. So we'll have 4 times we'll come to each of these, and typically we take a derivative of an expression when we have multiplication within it. Right, so we can rewrite that in this way. So here again our 4 terms. So this is, we take the derivative of psi here. So then we take the derivative of y here, right? So we'll soon talk about that, and then we'll dy2 and then dy3. And interestingly, and it's important to notice that this time derivative of the position vector dy1 of the differential, of course, dy1 with respect to time produces the velocity dy1, dy2, and dy3 components. Right, so this is nothing but dy1 with respect to taking the derivative with respect to dt. So so we have these interesting elements here, and so what now what we can do, we still can notice that we have this so we have this still these elements here, right? So which is nothing but dv. So we can divide everything by dv. This is this initial volume element differential dv, and so and we can now divide all of this by dv and pull it outside. So if I divide by dv, so this will be gone. So I will have only first term d psi dt here. Then I will need to divide here by all this combination. So here when I divide by dv, meaning that I divide by dy1, dy2, and dy3, and in that way we will eliminate this with this 2, and so we'll end up here with dy1 and divide by dy1, right? And in a similar manner we also will have the same thing here. So we'll have dy1 will eliminate and dy3, and we'll have dv2 divided by dy2, and so we can write it further in this manner, right? So that what will come out of here is that we'll have the psi still here, right? So it's always here, and then all the rest will come out, and the outside of the parenthesis is dv, but we remember that dv was just dy1, dy2, and dy3. And so we have here the so we have this expression, right? So we got rid of this multiplication with dy with different numbers, dy1, dy2, and dy3 in different combinations here, and so we have this combination here. So now we can look into what we have here. We have function psi multiply all of these, so I can pull it outside, but then what will be inside of the parentheses, that will be this very familiar structure for us when we take the derivative dy1, the sum of the derivative, that will be nothing but we can write it in index notation, right? So that will be dy dy right? And so because there are this summation of this, so we have these three terms, but this is nothing but the divergence of v, right? So we can write that was our divergence operator of v. So that's how we define the divergence operator. And again, d is small, so meaning it's so the divergence operator is taken with differential operator is taken with respect to the current configuration y, coming from here. And so then the first term is preserved, and then we can basically write, okay, so this whole second term is nothing but this, right? So again, so psi multiplying the divergence v, but divergence v is nothing but this dv1 dy1 plus dv2 dy2 dv3 dy3 in terms of the divergence operator. Now so here we also can recall that this, so we can look into this function, and we can recall how we can write this material time derivative. So we've done that before in our previous section. So to take material time derivative can be written in terms of the local time derivative and the convection changes, right? And so, and then in general, what we had here, that was the formula like that. Now, so we can use this general formula that we derived, and just basically here, instead of these dots, we can put our function psi, and now we can go after that. We can substitute this into so we can substitute this expression right here, and so now we can basically the first term will be partial derivative for local change of d psi dt, and then we'll have these two terms, this second term from here, right, and this grad phi v plus this phi divergence v. So actually we can combine them in a certain way, but to see how we do that, it's we can would be useful for us to write it in the index notation. So grad phi, we can write it d phi or d psi, d psi dy I, so this index, right, and multiply that with so this dot product, so the index will be the same, so vi, so that's the first term from here. All right, so let's put this arrow from here, and then the second term is will be plus, so we still have this psi, right, and then we have divergence v, which means that we have dvi dyi. Okay, so this is basically these two terms. So this second one right? Number 2, that's here, and then the first one, that is right here. Okay, so now with that we can notice that basically we can write this as a partial derivative with respect to y of a function of multiplication psi and vi, right? So I can basically write here that if I take the time derivative or the derivative with respect to yi of a function that is psi vi, right, then I will get this. So when I take the derivative, so that will be the first term, right, the d psi dy plus psi dvi dyi, so that will be second term from here. So so this whole so these two terms can be written just as one expression, one term here, and therefore we can rewrite this material time derivative dt ddt of this integral over the special function in the following way. So we have again, so the first term that we preserve here, right? So it's the first term is exactly the d psi dt, so it's still here, and then these two terms came and now exactly here. So right, but so what we did here, so we just noticed that the dd dy is can be substituted by the divergent signs because psi is a scalar and v is a vector, right? So then that can be represented as a divergence sign. Because what is here in the parentheses is indeed a vector, right? So vector v multiplied by the scalar psi. All right, so so this is an important formula for us. Now we can go ahead and basically substitute that psi here with the density. Right, so and then we can formulate the conversation of mass law for us. All right, so basically what we are going to say here is just the mass does not change at any point or at any part of the body, so it remains constant. So that's what we state based on our physical consideration, understanding of things. And again, the mass is is obtained by integrating the density over the volume, and basically again we can enclose any part of the material, so the integration can be around so can be over any piece of the any part of the material, any piece of that, and it still need to be constant. So this is our mass conservation law, right? Okay, what does it mean? So if that m is constant, so now if we're going to calculate the change of that rate of change, so meaning that we take the derivative, the time derivative of that, so we expect to obtain here 0, right? Okay, and that's where again our freshly derived formula 3.1 will become very useful. So, and again, so rho is mass density, and currently we're dealing with the mass density in the current, in the spatial configuration. Actually, later we will introduce the measure of the initial or density in the undeformed configuration. So, but now this is a function of our position vector y, right? And so, therefore, we need to use our formula for the material time derivative of a spatial function, And this is basically exactly the same operations we already performed for any scalar special function psi, right? So we take the material time derivative of that. So this is our integral of that produces the mass m, and now we do recall that, well, the integration is in the deformed state, in the current state of spatial description, so we need to take that into account. And because of that, it's not that we only obtain the first term, that is d rho, but also the second term that comes out of that, and before that we had psi divergent v. Now this is in the so-called integral form, so the mass conservation in integral form. And of course, what makes it the law is that we say that it must be equal to 0, so mass doesn't change with time. And so we now can go ahead and again repeat what we already have done for when the rank 311 is so we can again use this relationship and can write explicitly the material time derivative for any function, apply it to rho, and then we can write this formula 3.4 in this way. But what we also can do, we actually can state that because the choice of the where we integrate doesn't matter, so this law must hold true. This mass conservation law holds true at any point, at any part of the body. So we can then go from this integral form into the local form, basically dropping all the integrals after that. So we can write that we have this change, right? So so the change of mass is equal to 0, right? So and that is written in certain condition on the mass density rho. Yeah. So basically this is the local form of this part, right? So written exactly here, and and then we use this a few manipulations to write it explicitly, to expand our material time derivative of d rho dt into the special part and in the convection part, that grad v, and then combined with rho dv. So that would be our form for that. Now by looking into the first part here, again, this need to be equal to 0 for with our demand of mass conservation to hold true. Now, an interesting and important case for us is when the material is incompressible. And for incompressible materials, we'll see it later too, is that it can be shown by consideration of the properties of our. So again, I recall that the measure to what is incompressible material. So when dV divided by dV0, right? So the change in the volume. So when we say it's incompressible, meaning that the volume doesn't change at any point, and so that determinant f of J is equal to 1. So this is incompressible material for us, right? And we can show by considering those that actually for incompressible material, when J equal to 1, so this term divergence V needs to be equal to 0. So once you say that J equal to 1, that immediately drops this term as well, and then the mass conservation for incompressible material will be written as follows again. So for incompressible material, when J equal to 1, determinant of F, right? So the so then the mass conservation 3.5 reduces just to this simple formula like this. Okay, of course we can rewrite this by using 244 explicitly and write it that would be exactly as this part, because divergence V drops due to incompressibility, but and here you will just put rho, right? So because that is our consideration. I will consider rho, and then we can write in this way, or you can write it in a compact form like that. So, but this is only for incompressible materials, right? Because the additional term drops from that. And then again, so you can kind of look back and how we derive this term, where we consider the volume, and there was a rate and change in the volumes that produced us this term exactly. But if the volume doesn't change, so then we obtain this condition. Now, how important is this consideration of incompressible material for us? It is actually quite important because already mentioned that very briefly, but soft materials are typically considered approximated as incompressible materials. Of course, there is no such material as incompressible material, because that would violate certain physics. For example, pressure or longitudinal waves cannot propagate in such materials, and that's not what our knowledge about the physics of elastic wave propagation tells us. But because soft materials are so much easier for them to change their shape when we apply loading than to change their volume, and most of the loadings that we apply will just lead to the change of the shape, while the volume will not change. So, and therefore for us, because the volumetric change of the deformation is negligible, it's very convenient for us to consider them as incompressible materials. That will become important for us to consider and we will talk about that again when we start to postulate the materials law for that. But again, so this is important for incompressible material, that we have this constraint, and because of that we also have this form of the mass conservation. All right, so then we continue to the balance of linear momentum next.